In the last video, we talked about game trees and search in game trees, where we set up the formalism that we'll use to allow an AI to think about adversaries messing around in their search space. So classically, people will look at simple games like tic-tac-toe, but it's a little bit more fun to think about Connect 4. So Connect 4 is one of these games that probably everybody has played, at least when they were younger, but if you're like me, you probably haven't, you might not have played it for a while. It's one of these games that somehow faded from my interests as I grew up as a child. And what I discovered is that I started playing it again just for fun sometime after college. And when that happened, I realized that the game has a lot of complex strategy, more so than tic-tac-toe, but enough that you can imagine reasoning about the game in a mini-max style way that an AI would also think about. So for me, this actually somewhat ruined the game because as a child, I would just play it for fun, but then playing it once I gained more cognitive abilities just made the game much more stressful, and it was just me sort of staring at the board for minutes at a time trying to figure it out. But let me just walk you through a game that I played with myself, and you can start to think about what's happening in the strategy. So we start with the usual opening move. Blue throws down a piece off the center, and red plays in the center. And this is probably a typical start to the game where all of a sudden something kind of interesting starts happening here, where blue's setting up a diagonal. Um, Maybe I'm not sure that I really thought through what red was doing here, but now blue is playing something tricky. There's a threat on the board where there are three pieces in a row, and uh, blue's goal is to connect four blue pieces in a row. And as a counterattack, red sets up another threat on the other side where blue has to block. Blue is forced to block in this case. So as you watch this game, you'll probably start to see strategies and start thinking multiple moves ahead. And when you do that, what you'll notice is that, at least for me, my brain doesn't think that far ahead. And when it does think far ahead, it really doesn't consider all possibilities. I mean, if you look, I just had to look this up to draw this picture, but there are seven possible moves each turn, except for when you get near the end when it becomes less. But for the most part, there's seven possible moves. But most of those moves don't make sense. And our brain very quickly prunes those away. And in reality, we probably prune things away over aggressively because there may be surprising strategies where we go someplace far away from where the action is, and that actually works better. All right, so in this game, red just had to block blue from yet another threat to win the game, and things are starting to look a little bit bad for red if you are following, right? So there's still that diagonal threat on the board, and blue's going to play here, and then it sort of hints at another possible threat coming up. So red counterattacks and sets up a threat to complete a four in a row, and blue is forced to block there. So if you stare at this board long enough, you'll see that there's lots of possible bad moves now for red. And I suspect, I haven't done out the whole tree, but I suspect red has already lost the game, but I'm not completely certain. But based on my intuition, my best move that I saw for red was to block this corner piece right here to avoid immediate losses or immediately setting up a trap. But then blue can simply play a slightly tricky move, which is this, which forces red to block, which will set up that diagonal that was set up way long ago. So red's forced to block, and then blue is able to win the game. So the point of this is not that you're watching any grandmaster play or anything. I basically played relatively randomly without thinking too hard about each move. The point is that as our brains, as humans, were looking at the game, we were doing things like deciding whether it was worth our time to really think about all the possible moves, expanding the full game tree after each individual possible move. And that's what we want to instill into our AI algorithms to make them operate faster, so they don't have to expand exponentially sized game trees to decide on relatively simple decision situations. And as I mentioned, we're going to try to do it in a way that guarantees that the AI won't over aggressively prune, which is a little bit different than how humans do it. Humans will often over aggressively prune and therefore remove possible strategies from our thinking that a computer may be able to discover. Let's walk through what happens when we run Minimax in order. Like, we'll step through the algorithm. Okay, so pretend we're at this state. We're currently at the state where we have explored the entire subtree of the B state. So again, we already did this a few slides ago. So pretend we're trying to compute the Minimax move for state A, for coming from state A for the max player, and we considered action A1. We did the minimax procedure, and we computed that 3 is the minimax score for B. Okay. Now we're going to continue. We're going to continue the algorithm, and the next step is then to try action A2, taking us to state C. And then from state C, we're going to now try action C1, taking us to this terminal node, which has score 2. So we now know that, C, our sort of our temporary variable for choosing the minimum value of all the actions available from state C for the min player, right, is currently set to 2. Okay, now we continue, and then we see another terminal state by taking action C2, and we see that it has score 4. And then at this point, we don't actually update our temporary variable because 2 is the lowest value we've seen so far, and 4 is higher than that. 4 is a greater number than 2. Okay, and then similarly, we see C3, and we get utility value 6, and see that's greater than 2. So 2 is our value. Okay, so let's think about what just happened, right? So we saw 2, in the first step, and there's actually a clue. There's actually a way for us to tell that we should stop after that. And why is that? That's because remember what our goal is, right? At the top level, at the very top level, we're trying to solve the find the maximum scoring minimax move for the max player. Okay, and so you can even imagine, even in some scenario where we change the scores, instead of having 4 and 6 as the next two states coming from C, we can put them even lower. They could be lower than 2. They could be 1 and 1. So now, if we really wanted to find the minimum value, the minimum scoring state from C, we would have to at least consider C2. But if you think about it, once we've seen 2, once we've seen the action C1 to the state that gives us a utility score of 2, we already know that A1 is a better action for the max player than A2. Right, so the reason is, again, the max player is trying to pick a minimax value that is as high as possible. And action A1, we've already figured out by exploring the entire subtree of B, that action A1 will give us a minimax score of 3. And then action 2, we discover that there's a way for the min player to score 2, to make the utility value 2. It doesn't matter that the player can also make it 1. The min player can make it even worse for us, but already, because the min player can make it 2, it's a worse move than A1. A2 is a worse move than A1. So for the sake of making this example work a little bit better, I'm just going to reverse the order of the moves from D. So if we look at the third branch and we consider that the nodes have been reversed, again, we have the same situation. We see that from D, the min player can make a move that gives us a utility score of 2. And so in the same way as things are progressed from state C, it doesn't matter what the other moves are available to min, right? Because we already know that min can make a move that makes the branch, that the result of the game that happens after state D worse for the max player, worse for us. We're the decision maker as the max player. Worse for us than if we were to take A1. Okay. And so this is the basic intuition behind alpha beta pruning. But the key is that alpha beta pruning is a little bit different. What we just did was just sort of walk through the thought experiment if we're the max player and we're trying to prune. But alpha beta pruning is trying to prune both as the max player and as the min player. And it becomes important in deeper trees, right? Here we only had a 3-level tree. And so what it does to handle both the min and the max pruning is that it's going to keep track of 2 numbers for every single node. It's going to keep track of the alpha, which is the highest value choice along the path, and beta, which is the lowest value choice along the path. And then the whole strategy is built around comparing the alpha and beta values of different nodes and different subtrees to decide whether we need to continue searching any particular subtree. So let's go through the example that's in the figure from the book that I copied here onto this slide. So it starts out with, it's the same tree that we looked at before, but the important thing is now we're going to look at how we implement it with this upper and lower bound, the alpha and the beta. So when you start out, the root node has an alpha and beta of minus infinity and plus infinity because we haven't seen anything, so we can't say anything about these are like the worst case, right? So remember the first term is supposed to be the highest value node that we've seen on the path, and the second term is the lowest value. And right now we set them to infinity as basically sentinel values. So when we look at state B, we see that has a alpha value of minus infinity still, but it has a beta value of 3. Now, what does that mean? It means that is so far that is the lowest scoring node that it's seen along its path. Or rather, it's the lowest node or lowest value node that uses B on its path up to the root. Okay, and then as we continue searching, we're going to look at the next sibling of that state that gives us score 3. So it's 12, and so that doesn't change our values, right? It doesn't change the 3 because 3 is smaller than 12, and then similarly 8 doesn't change the value. But what it does tell us now is that we've now explored the entire space of possible states that we can get to from state B, and now we can say that the highest value, the highest minimax value that we can get to from state B is also 3. In other words, right, when we see that the 3 is the alpha and the beta value, we've actually found the exact minimax value, right? And so this should give you a clue as to what these alpha and beta values are, right? Because they're upper and lower bounds. And if you think back to where we were before, we initialized them to be minus infinity and plus infinity, which basically translates to, all we know so far is that the minimax value for this state is something in between minus infinity and plus infinity, which is all all real numbers. So instead, as we start exploring, and in this case we've explored the entire subtree around underneath state B, we can get the exact minimax value, which is 3. So now we've sort of sandwiched with upper and lower bounds of the exact same value. And because we now know the minimax value for state B, we can propagate that up and think about, what do we now know about these alpha and beta bounds for state A? Okay, and what we know is that we've seen a state that has minimax value of 3. So the lower bound has to be at least 3. Right? If we find another state that's better than 3, then it'll increase that lower bound. But for now, we've seen at least we can get score 3 if we choose state B, right? If we choose the move that takes us to B. So far it's not all that interesting, but then things get interesting when we start looking at other branches. So now when we start looking at state C, we look at one of C's possible children, and we immediately know that the min player's upper bound is 2. Meaning that the min player has at least an option as good as 2. Now it might be to get an even better option if they can find an even lower value than 2. But just like we talked about in the last example, which is the same example but without the lower and upper bounds, we already know something here, right? Because the min player can score 2, which means that the upper bound, the maximum possible minimax score that you can get to by choosing a move that takes you to state C, is 2. And we already know that we have a move better than 2, right? As the max player, we have a move that's better than 2, that's bounded, or rather, the lower bound for the move that we're considering is already lower than our upper bound for the minimax score of A, which means we no longer need to consider searching this subtree because it can only that gap can only widen, right? We've already found that the current state we were considering, or the current path that we've considered that we've seen so far as we look down the path going through C, is already telling us that this score is too low. This score is too low for us to consider. And when we continue looking, we're going to find even lower scores, or we'll find the same score, but it can only get lower. So we can immediately prune this away, or rather, we can just move on from this branch. We don't need to consider it anymore. So instead, we can move on to what happens if we go to state D. So the first thing that happens when we go to state D is we see that there's a possible utility score of 14. Okay, and that means that D's upper bound is now 14, right? There's no way that the min player, now that there's at least one score of 14, the min player can only choose a move that's going to be better than 14. Okay, and then that also propagates up, because that means that as the max player, you can sort of see that this looks like really good news, because now all of a sudden there's this option that based on just the tree that's on the screen right now, pretend you don't remember what the tree looked like before we sort of hid some parts of it. It looks like there's a move that might get us as the max player a score of 14, which is way bigger than what we thought before. Right? We thought the best move we had was 3, or had a utility value of 3, and now we see that if we go to D, if we take the move that takes us to D, the min player has a move that's going to give us a score, or give the total score of 14. Okay. But then the diagram skips ahead in the book, for the same reason that I sort of reversed the order of those nodes, and you'll see that eventually, once you expand or explore all the nodes of D, you discover that D has a minimax lower and upper bound of 2 and 2, meaning its minimax value is exactly 2. And the algorithm wouldn't discover this until it finds that node down there that's 2. And so, you can imagine if you ran the whole algorithm, step by step, what would happen is the max score, the max player would sort of see, be very hopeful, when you see a score 14, that, okay, maybe there's some lucky way that 14 is the value we're going to get. And then you check out the next node when you get a score of 5, and that lowers this upper bound, and the max player now says, okay, well, maybe we'll get 5. And similarly, the min player thinks that maybe 5 is the best that we can get. And finally, you see the 2, and we've explored the entire subtree underneath D, and we know the exact minimax value of D. So this is the whole diagram. You can see the steps of the algorithm. And looking at this diagram, it's not completely obvious, at least to me, how to implement this. Now, it's straightforward once you have somebody write out the pseudocode for you, which the textbook has done for all of us. But if you just look at this diagram, things get a little bit hard to keep in your head. Right? We've managed to keep track of the, we keep track of the numbers, the alpha and beta numbers, but then where the decision points are for when you compare them and when you decide whether to prune away or ignore part of the rest of a tree is a little bit tricky, or at least to me it is. So we can stare at this image for a bit and try to think about where we should be checking the upper and lower bounds, and what are the pairs of states we should be checking. And one intuition is that we should definitely be checking something, one of our ancestors, right? Either the parent or something that is above us in the tree along the path to the current state. And we sort of have this intuition, which turns out to be incorrect, that what we should be doing is we should be comparing one move to another move, right? That's sort of what we did when we sort of did the example out and just sort of drew it on the screen. But it turns out that that's not the best way to do things, or at least it makes things more complicated than they need to be. Instead, by this whole concept of storing the alpha and beta, bound upper and lower bounds at each node, we don't have to go back and look at alternate moves or look at previous moves that we've already considered. So, for example, if you look at subfigure D in this slide, this was the key scenario. This was the situation where we are exploring possible moves for the min player from state C, and we've already previously looked at all of the details, all of the possible moves for if we go to state B. And intuitively, again, it sounds like we're comparing a move to C to a move to B, and we're kind of doing that, but it's very implicit, because all we have to do instead is compare the move to C to whatever is stored at the parent A. Okay, and this is how the pseudocode works. So it's very similar to the code I showed you before for minimax search. Again, we're using this is looking at the book pseudocode, which explicitly separates out the max method and the min method. But in this particular case, it actually makes things more convenient than if they were sort of jammed into one single method, just because we treat the alpha and the beta values differently depending on if you're the min or the max. So the key line of code you should look at is what I've highlighted in blue, which is, let's just look at the max value method for now. It says that if v, which is sort of this, okay, so backing up, v is the temporary variable that we're using to hold the maximum value we've seen so far as we explore the possible moves from this state. So if v, the temporary variable, is greater than beta, then we return v and just stop the search. We don't continue looking at the other possible moves that we haven't yet explored. So looking back up, what is beta? Well, beta is going to be the lowest value that the parent has seen so far. And what this means is that, in the middle of, or probably before, all the actions have been explored, we've already seen a, max player move that is better than the minimax, or the sort of the bound on the best minimax move for the parent, which in this case would be a min player. And so the reverse logic occurs in the min value method. And then, the other thing to keep in mind is how we update these values. So after we discover a value that is greater than, for example, our lower bound, then we would update our alpha value. And similarly, if we discover a value that's less than our upper bound, then we will update our beta value down below. So that's the pseudocode, and it's a kind of a simple idea, but it's pretty hard to get things flipped. There's a lot of upper and lower bounds. There's signs of what you want to be greater than or less than other pieces of the the data that we're storing. It's pretty easy to get tripped up with this stuff. So I admit that I'm getting a little confused going through this myself. Usually you can see right away by running through a couple examples whether you have one of these inequalities flipped. But it's like I said, it takes a little bit of work. So we'll go over this in class. We'll talk more about how this can be implemented, and go through some examples maybe if that's going to be helpful for you. And then we'll also talk about some other things. So there's a few things that are in the textbook, a few concepts that are interesting to think about. So one is a transposition table. So the concept of sort of having a cache of previously seen states and looking up in the cache before you go and compute minimax. Maybe you've already computed the minimax value for that state already, so you can look it up and it saves a lot of time. That's the situation where it goes a step in a different direction than AlphaBeta pruning to make things faster. And you can imagine how this can be really important, especially in games where there's an infinite search space. Like you can imagine in chess, where you have moves, players or pieces that can move back and forth. They don't have to be, they're not like pawns where they can only move forward, but they can move in multiple directions. Like queens. You can have repeat states all the time, right? So when we think about doing a search to find a terminal state, there's going to be paths that go on infinitely. Assuming you don't have like a draw rule, like in chess. And so, having a cache can prevent you from, recomputing the minimax value for a state you've already seen before. Okay, and then similarly, another way to handle situations with very deep search trees or with infinite search trees is to have maximum depth heuristics. So you basically say, I'm going to run minimax, but I'm going to keep track of how deep I've been searching in the tree. And once I reach some maximum depth, maybe it's determined by how much memory we have, or maybe it's determined by some time limit. We're just going to run some heuristic on the current board state or the current game state, and try to determine the scoring, the scoring payoff, the utility value based on a heuristic, based on a guess. And so this is where, in the first class we talked about how we could come up with a performance metric for chess. And one of the performance metrics is these, again, heuristics, where the real bottom line is whether you checkmate the opponent's king or not. But along the way, you have heuristics like the value of the pieces on the board, the amount of space you control, the amount of tempo you have. And that's where these heuristics can come into play.